So we are going to start three-phase induction machines. Three-phase induction machines is a broad category for both motor as well as generator. So we'll be talking about three-phase induction motor first. It comes under the broad category of AC machines because it runs on AC. And the AC machines here are essentially of two types. One are the synchronous AC machines and the other one is asynchronous AC machines. Now, synchronous AC machines are those machines which run on synchronous speed. They run at synchronous speed or not at all. Now, this synchronous speed is notated by ns, and it is essentially the speed of the rotating magnetic flux or field. So synchronous AC machines run at a constant speed, and what is that speed? It is the speed of the rotating magnetic flux, which is the synchronous speed. Or they do not run at all. They run at synchronous speed or they do not run. The other category, which is the most commonly used category, is the asynchronous AC machines. These asynchronous AC machines, they do not run at synchronous speed. An induction motor is a type of asynchronous AC motor. Machines is a broad category which essentially is a term which is used for both motor as well as generator. So induction motor is a type of asynchronous AC machine, and 90% of the motors used in industries are your three-phase induction motors, because they have certain qualities which make them more compatible to industrial use, because they are very rugged and very inexpensive. So three-phase induction motor, they run, as the name suggests, it runs on the principle of induction. So I'm assuming all of you are familiar with transformers. Transformer is another machine which runs on the principle of induction. That means whenever you give supply to the primary of the transformer, in the secondary an EMF is induced, because they are magnetically linked with respect to each other. They are electrically isolated but magnetically linked. But in induction motor, what happens is you give supply to the stator, and the rotor has an induced EMF, and that induced EMF in turn causes the rotor to move. We'll see how, but this induction of EMF is the same. So that is why this is called a three-phase induction motor. Now this is a sort of rough diagram of a three-phase induction motor, where this is the stator, and the stator is supplied with a three-phase AC supply. Whenever a three-phase supply is given to a three-phase motor, this is wound for three phases, and when a three-phase supply is given to the stator terminals, a three-phase rotating magnetic flux is going to develop. So what happens is, you can see that the three-phase rotating magnetic flux is being developed. Okay, and this flux or field is rotating at ns. As introduced earlier, ns is the synchronous speed. So the speed of the rotating magnetic flux is the synchronous speed. Okay, now what happens? You give supply to the stator, a three-phase field is set up which is rotating in space, and what is the speed of this rotating magnetic field? It is equal to ns. But this ns cuts the stationary rotor conductors. You can see these rotor conductors. So they are stationary while the field is moving. So a rotating magnetic flux is there and a stationary conductor is there. So according to Fleming's law of electromagnetic induction, it is called EMI, electromagnetic induction, Fleming's law, and EMF is induced in it, and that EMF causes a current to circulate in the rotor conductors. They are short circuited onto themselves. So that is why, because they have short circuit, a current is induced, and whenever you have current, you will have a force. Okay, so electromotive force is set up, and that force will cause the rotor to move in the same direction. It will start moving in the same direction as that of the rotating magnetic flux. If the rotating magnetic flux is moving in anti-clockwise direction, so will be the direction of rotation of the rotor. So this is the rotation of the magnetic flux, this is the rotation of the rotor. So it will also start moving in the same direction. Why is this so? This is due to Lenz's law. Now what does Lenz's law state? Lenz's law states that the effect, that is movement of the rotor, the movement of the rotor will oppose the cause. What is the cause? It is the speed difference between the rotating magnetic flux and the stationary rotor conductors. The magnetic flux is rotating, so speed is ns, and so far the rotor is not rotating. So what is the speed of the rotor? It is equal to 0. So what is the speed difference? It is ns. So it will try to bring down the speed difference. So how it will try to bring down the speed difference? It will try to move in the same direction as that of the rotating magnetic field. Let the speed of this be equal to some n. Okay, so this n is going to increase, and it will the essential speed difference ns minus n is called the slip speed. This slip speed is going to decrease as the motor catches up speed. Okay, so this speed is the slip speed is going to decrease, but it will never be equal to 0. It will be 0 in what circumstances? When n is equal to ns, but it will never be equal to 0. Why? Because the rotor conductors are not moving in space, the field is moving in space, so it will have some kind of losses. So mechanical losses are there, so rotor will never catch up with the rotating magnetic field, and also the law is there. Okay, so it doesn't mean it is going to catch up with that. It will start moving in this it will try to bring down the difference, but it will never exactly bring down the difference to 0. Otherwise there will be no torque developed in the motor will come to a standstill, because it is essentially the slip speed or the difference between the rotating magnetic flux and the standstill rotor which is driving the torque of the rotor. So now the motor also starts moving in the same direction, so the motor also starts moving. So this is essentially the working principle of a 3-phase induction motor.